Shambhunath Group of Institutions, shaping the future.
Students, good morning. Today we are going to discuss that is hybrid coupler. Before this lecture we had discussed about the directional coupler, two-hole directional coupler. Now another directional coupler which is in your syllabus, that is hybrid coupler. That hybrid coupler we are going to discuss today, and its diagram we have already drawn, and this diagram says here you see a hybrid coupler. What we are doing onto this, on a printed circuit board, the microstrip patches are cut in such a way so that they can be connected by the strip lines, and these all the strip lines can be joined by some means. Here we have drawn the hybrid coupler of 4 port, that is port 1, port 2, port 3 and port 4. These are the strips which have been fabricated and designed over the printed circuit board, and in the printed circuit board on the upper side, this is the diagram of the copper cladding, and underneath this one copper plate is there which will act as a ground, and here this hybrid coupler is connected by one this strip and another this strip, and these are the small lines, these are the small width lines through which these all the ports have been connected, and they have been connected in such a way that whatever the energy, we try to understand the function of this operation of this hybrid coupler. When we provide input onto this port P input, then this power is routed onto the port 2 and onto the port 4. But the division of this power is such that whatever the power at port 2 is there, it will have the same phase as it was of input power, and the phase with reference to this port of the power at port 4 is pi by 2, 90 degree. The difference between the phases of the power at the port 2 and port 4, that is of pi by 2, and thus we call it 90 degree hybrid coupler. 90 degree hybrid coupler. And this 90 degree hybrid coupler, they are also termed as 3 dB hybrid coupler. 3 dB hybrid coupler. Similarly, what happens if we provide the input onto the port 2, then the power will be routed onto port 1 and port 3, but no power will be routed onto the port 4. As we had discussed, that if we are applying the power in the input port 1, then this power will be routed onto this port 2 and port 4 with a phase shift of 90 degree at port 4 and 0 degree at port 2. Whereas the power from the port 1 to this port 2 is very minimum coupled, or we can say it is negligible power which is getting coupled here. P3 is approximately 0. So this is very less power which is getting connected. Thus, similarly we can use this hybrid coupler in any way. If we are considering this port 4 if for input, then the input power is, suppose we are feeding the input power at port 4, then it will be divided onto this port and onto this port means at port 3 and port 1. At port 3 it will have 0 degree phase shift, and at port 1 it will have 90 degree phase shift. So this hybrid coupler is reciprocal. Okay. So, and this hybrid coupler is used if we talk about the applications, that is on the balanced amplifier and the balanced modulator and the mixtures and attenuators. Here we have shown this balanced amplifier where we have used this hybrid coupler, that also known as Lenz coupler. Lenz coupler. This hybrid coupler also is known as Lenz coupler. Here we have drawn an amplifier, balanced amplifier, where we have shown the use of Lenz coupler at the input side of this amplifier and at the output of the amplifier. The input of the amplifier, they are termed as port 1, and at output side the port, they are termed as port 2. Whereas here, if we see this hybrid coupler, this is the symbol of this lines diagram is the symbol of this hybrid coupler, which is having four ports. Here what we have done, that at port 1 it has been connected here where input is fed, and port 3 of this coupler, port 1 and port 3. Port 3 has been terminated by 50 ohm impedance, whereas this power is routed onto this port and onto this port. As we have considered here, that when the power is fed, then some of the power is going on to this port, okay, on port 2 and port 4. So similarly, this is port 1, this is port 2, this is port 3, this is port 4 of this hybrid coupler. So we can see this is hybrid coupler port 2 and this is hybrid coupler port, that is port 4. So the power may be available here in 0 degree phase shift and 90 degree phase shift. So for this it is conducting, and when it is conducting, then the output, when one amplifier is conducting, then the output is available onto this, and when this will conduct, then output will be available onto this. So this port power output is derived from this port 2 and this port 2 dash. So the power may be connected here and the output can be taken from this port. We can see this is again, here is port 1 of this coupler and this is port 3 of this coupler. We can see port 3 and this is port 2 if we see, and this is port 4. So by keeping the operation in mind, we can have the analysis of this coupler also, and here the power which is available at port 2 or port 4, and this again port 2 has been terminated by 50 ohm impedance. So by keeping this in consideration, we have drawn some of the scattering parameters, that is reflection coefficient at port 1. The reflection coefficient at port 1 of this amplifier is S11. The reflection coefficient of the power of this device is termed as S11A, and this S11B is the reflection coefficient of this device, and here is S22A. S22A means this is the A device, here we will have S22A, and S22B will have onto this port. So by taking the difference of these two reflection coefficients and taking the average, then we are having S11 parameter, and S22 parameters are also achieved by taking this parameter S22A and S22B, and we are minusing them, then we are dividing it by 2. So we get S22 and S11 both. So the important parameter is VSWR for the input port, and VSWR, as we are knowing that VSWR is nothing but the standing wave ratio, and standing wave ratio is the health measurement for the amplifier here. So this will be depending upon S11 and S22 for the output port. For the input port, if we talk about this input port, then VSWR for the input port is calculated by this formula, and for the output port we have the calculation by this formula, that is VSWR is equal to 1 plus S22 divided by 1 minus S22 for the output port. Here the gain is S21 square parameters, and this also is usually written as gain in dB is equal to that 10 log of P out to the P in power to the base 10. So thank you for this. We'll see next topic. We'll see the next topic. Okay. We'll see the next topic afterwards. Close it. Now we are going to discuss about the circulators, and in this circulators the important phenomena is the Faraday rotation. So we'll have the phenomena, that is Faraday rotation, and then we'll discuss about the circulators through which the waves can be rotated in one particular direction. Okay, so have this look. Faraday rotation. If we talk about the Faraday rotation, one Farad rod is taken. One Farad rod is taken on some particular length and some particular radius or diameter. Here we apply the magnetic field, DC magnetic field. We apply the DC magnetic field. Okay, DC magnetic field, DC magnetic field. This is magnets we call. These are the magnets. So we say these are the magnets. Cross section of the view we have taken. Here when we apply the EM wave, we apply the EM wave. Considering the vertical polarization, then when this EM wave is passed through this ferrite rod, that is ferrite rod, it provides a tilt or rotation in the EM vector by some particular angle. This device is non-reciprocal. It means when the wave moves from our right hand side towards the left hand side, then suppose the same wave at this particular angle anyhow rotates, then this will have the rotation by the same angle, by the same angle, by the same angle theta in the same particular direction, in the same particular direction. So what we have discussed, what is Faraday rotation? What is Faraday rotation? Faraday rotation is the phenomena, we can write it, Faraday rotation is the phenomena in which the applied EM wave will be rotated under the effect of applied DC magnetic field as the wave propagates through the Faraday rod of certain length and the diameter. I feel it might be clear to you. That is what is Faraday rotation. Now you see in this example what we have done. This is Faraday rod. Faraday rod is that metal oxide, divalent metal oxide Al2O3 material, and in this Faraday rod the EM waves is propagated or passed through this, and we are seeing that the electric field has turned with reference to this reference line by angle theta in clockwise direction. And similarly, if the same wave anyhow is reflecting back, then this will have the same rotation but in the same direction, clockwise direction. Means what? Here it has the property to rotate this electric field vector in the clockwise direction. When it is passing through this, again it will rotate the vector in the same direction but not in the anti-clockwise direction. Okay, so that is Faraday rotation. Why it happens? The reason being, when we are passing this EM wave through it, the dipoles available in this Faraday rod, they are aligned, and then that alignment of that molecules or unpaired electrons, that is pressurizing this electric field vector to rotate in one particular direction. That is the reason. So by having this Faraday rotation property of the Faraday rod, we are going to discuss the circulator, and as we have discussed, that is directional coupler. So we'll use the directional coupler as well as this ferrite rod for the phase shifter. So this is nothing but one phase shift has occurred, and the same thing will be applied in the isolator principle. So we'll have the circulator here. We'll see the circulator. As the name suggests, circulator means what? That whatever the power we are feeding at one particular port, that power will be rotated in one particular direction. That is in one particular direction. Here we have drawn that 4-port directional coupler, port 1, port 2 and port 3, and this is port 4. So suppose the EM wave has been applied onto this port 1, and if we are having the ferrite rod available here and it is giving a shift onto this ferrite rod and onto this, and it is pressurizing this EM wave to rotate in one particular direction, that is in clockwise direction. So it is rotating in the clockwise direction. It may be received at port 2, and from port 2 it will be traversing towards the port 3 in the same clockwise direction, and from port 3 it may be routed to port 4, and from port 4 again it has to come back onto port 1. So the direction of rotation is clockwise. By using one particular ferrite rod, if this ferrite rod or ferrite material is changed, then only the direction of the EM waves will be changed. So it is, if it is required that clockwise rotation, then as per the requirement of the rotation of the EM wave, this ferrite rod is constructed. If it is to be rotated in anti-clockwise direction, then that ferrite rod will be changed. Ferrite rod will be changed. Here we see that this is ferrite rod. So the power may be routed in this direction also, in the clockwise direction. Similar, by using the same principle in the clockwise direction. This is in the anti-clockwise direction. So from port 1, port 2, port 3, and this is port 4. Here, as the name is suggesting, circulator. Circulator means it circulates the EM wave in the device from one port to another port, another port to another port, and then similarly in the other direction. In the same one direction it is rotating. If we have to have rotation in the anti-clockwise direction, then this ferrite material is to be changed. So this ferrite material is for the clockwise direction, and this ferrite material is for the anti-clockwise direction. So we can write it is the clockwise and this is anti-clockwise. How it is implemented, we'll see by the phase shifters and by the directional couplers. So circulator implemented with the help of with the help of that is directional couplers and with the help of phase shifters provided by Faraday. So for a particular phase shift, for a particular rotational angle, this Faraday rod is to be constructed. Okay. So here we are having one schematic diagram for the circulator implemented with the help of directional couplers and the phase shifters. Let us consider this diagram here. I am omitting this diagram and then we'll see by having a clear picture that what we are doing. So see that one waveguide is there, another waveguide with the two holes that is supported here. This is one primary waveguide. This is the cross section, side view, and another waveguide is here that has been joined at the bottom side. Here in the two holes, we are arranging two directional couplers, directional coupler 1 and directional coupler 2. Two directional couplers we are arranging. This is primary waveguide or main waveguide. And this is secondary waveguide or auxiliary waveguide. Auxiliary waveguide. Here we termed as port 1. This is port 2. This is port 3. This is port 4. And here we are having phase shift aligned in it. In the main waveguide, one phase shifter is there. It means it is made up of ferrite rod, and another phase shifter is there. That is again made by ferrite. These phase shifters have been arranged in such a way that in forward direction, it provides a 180-degree phase shift to the wave, incoming wave, and when the wave is returning from port 2 side, then it will be giving a 90-degree phase shift. Similarly, second phase shifter, it gives 0-degree phase shift to the flow from port 2, from port 3 to port 4 in the auxiliary waveguide, and again in the reverse direction it provides a 90-degree phase shift. So we are having two directional couplers, and here the phase shifters are there. Phase shifters are there. Here we have arranged one directional coupler which gives a phase shift of 90 degree. This directional coupler is also giving a phase shift of 90 degree when the wave passes through it. So we are going to have the operation of the circulator. It is the circulator implemented with the directional coupler, phase shifters, and two waveguides. Connected as shown in diagram. So if you see, let's take the EM wave propagation through the circulator, how it is propagating. Suppose we apply the source at the port 1. The power is input, incident power is taken here, input power or incident power we say. This input power of the EM waves is trying to move or it is flowing. So it has to go on to port 2 from port 1 to port 2. When it is going from port 1 to port 2, now see this wave, when it is passing through this, it will have a 180-degree phase shift. This wave is not propagating through this hole or through this hole, so the directional coupler will not give any phase shift to this wave. Only the phase shift will be assigned by this phase shifter to this wave, that is of 180 degree onto this port. Now the wave, this wave may be routed, you see this wave may be routed to this EM wave, that is phase shifter, which will provide 90 degree phase shift, and it is again routed onto this. This phase shifter is providing a 0 degree phase shift to this wave, and this directional coupler again it is providing 90 degree phase shift. So both the phase shifts are added, and here again we get onto this wave, wave 1 to 2, and this is wave 1 through hole through TC coupler 1, and then 0 degree phase shift, then again direction coupler 2, then at port 2 we can see. So it means the wave is traveling on to port 1, port 2, that is available at 180 degree, and the wave which is propagating through this auxiliary waveguide through the two directional couplers and the one phase shifter, it will have a phase shift of 180 degree. Both the waves, if we compare, then the phase shift between the both the waves is 0 degree, that is 180 degree minus 180. So that is of 0 degree. If we add them, then also it will be 360 degree, which is same as 0 degree as the cycle completes. So we say this is 0 degree or 360 degree is the same as we see this circle from here. If we start at 0 degree and again we come back onto the 360 degree by having a rotation like this. So the phase shift is 0 degree. Now the wave which is passing onto the port 4, how it is passing? Now the same way, when it is traveling through this, and if it is to be routed onto the port 4, then this wave will be routed onto this. Here 180 degree phase shift has been provided, and now this wave is traveling through this directional plug. So this is provided 270 degree phase shift. Here 270 degree phase shift. This is 180 degree phase shift onto this wave, and this is 90 degree phase shift provided by this directional coupler 2 onto this, and we get here the wave from 1 to, that is 270 degree. Again, this may also move through this. Here suppose this is the wave which is routed onto the port 2. If we have the direction of this wave onto this part, when it is not traveling through the hole, that time it is 90 degree phase shift given, and here it is given, that is this is 90 degree, see this, and this is 0 degree phase shift. So the wave will be given, wave will be routed onto this direction, and this will have a 90-degree phase shift. So if we talk about, that is the phase shift available at port 4, this is at port 2, this is at available port 4. So 270 degree minus 90 degree is equal to 180 degree. It means what? That wave which is available from port 1 to this phase shifter, means from port 1 through a phase shift of 180 degree, then through a phase shift of 90 degree, then it is reaching to port 4, and the wave which is coming from this, that is from port 1, then through the phase shifter of 90 degree, then through this 0 degree phase shifter, and then it is available onto port 4. So if we see the phase difference between them, it means at port 4 the wave will not be received, means cancellation of wave will be there. It means what? That what we are saying, if we have made a circulator which is moving from port 1, then this port 1, it will be routed to port 2, port 1 to port 2, which we have received it here. It is in phase, so the powers are added. And we achieve the wave in phase. But if you see, this is a port 4 and this is port 3. If we see, the flow of power from port 1 to port 4 should not be there, because it is a circulator and it is circulating in clockwise direction. So it must come from port 1 to port 2, port 2 to port 3, but it cannot be directly routed from port 1 to port 4. So when the power is routed from port 1 to port 4, that time this power is getting cancelled, because they are 180 degree out of phase. Suppose there may be a probability that if the wave is coming from port 2 to port 3, if we see it, then the wave which is returning from port 2, suppose some wave is coming from port 2, then port 2, it will have 190 degree phase shift in this direction. Suppose we have another wave coming from port 2. So this will come here having a 90 degree phase shift, and again it will be routed onto this, and there will be 90 degree phase shift. So here 180 degree phase shift will be there for this wave which is traveling from port 2, means this wave is traveling from port 2. Here we can say it has traveled from port 2, then 90 degree phase shifter, then it has come again 90 degree phase shifter, then it is available at port 3. Suppose from the same port 2 there is another probability that the wave may be routed through this hole. So if the wave is coming through this hole and coming here, it will have a 90 degree phase shift. Again it will have a 90 degree phase shift. 90 degree phase shift by this direction coupler DC2, and the 90 degree phase shift by this phase shifter in this direction, and then here we are having again 180 degree phase shift. So this from port 2, it has undergone a phase shift of 90 degree, and again a 90 degree phase shift, then it is available at port 3. So here the phase difference between the two waves, again we have del phi 3 is equal to 180 degree minus 180 degree, that is 0 degree phase shift, and the waves will be added. It means what? that wave can be routed from port 1 to port 2 and port 2 to port 3 in phase. If the wave is to be routed from port 3 to port 4, that will be available. Suppose we say that wave is traveling through this, then one wave is having a diversion through this medium, through this hole, through this direction coupler, that is 90 degree phase shift, 180 degree phase shift, then 90 degree phase shift means 360 degree phase shift. It will be available here from port 3 to port 4. And another wave may have another path which may travel through the phase shifter, 0 degree phase shifter, and it is having a 0 degree phase shifter only. So we say that the waves when routed from port 3 to port 4, 3 to 4, they will have 360 degree phase shift and 0 degree phase shift, which means that is 360 degree phase shift means again 0 degree phase shift, and so the power will be at. It means the power can be routed from port 1 to port 2, port 2 to port 3 and port 3 to port 4. But they cannot be routed like this, port 1 to port 2 or port 1 to port 4 in other direction. So here this direction coupler has been implemented and it has been implemented by these two directional couplers and by two waveguides and two phase shifters, we can say, and which are providing the phase shift in forward direction of 180 degree, and this is providing the phase shift of 90 degree in the reverse direction. Here it is giving the 0 degree phase shift and it is giving the 90 degree phase shift in the third direction. That's so. And this directional couplers are again used at the last stage of the RF amplifier, means when the antenna is connected to the transmitter. If we see this circulator, how it is provided. If we see this circulator can be applied into the transmitter onto this last stage, RF amplifier stage, where we can have 3 ports, means we can have one antenna to be connected here, another antenna to be connected here, and we can have the sample from here, and then we can utilize this circulator at the end, and the same circulator can be used for making the isolator. Okay, so the application, if we call out the application, then applications. Number 1, in the RF stage of transmitter. And another application, that isolator may also be implemented. By the same. Okay, thank you very much. Next topic उठा लेते हैं. Welcome back to the session. Next session, that is for the Faraday rotation isolator. This Faraday rotation isolator, as we have already discussed in lab, that isolator prevents the reflected wave which are generated due to the mismatch of the load impedance from the source impedance. If there is any mismatch, then the power is reflected back from the load side towards the source side. The power which is getting reflected back, that may damage to the source. That's why one device is required which can isolate those reflected powers from the source in the forward direction. That will see how it is going to function. So in this we are having some components, that is one waveguide portion, that is a twist. This is the waveguide port. Here we'll see, we'll discuss it. As you see this is the direction of propagation we are assuming. Here we are having a plate. We are having a conducting plate. Then we are having a ferrite rod for a particular rotation of the EM wave. Then again one plate is there which is tilted at 45 degree. From the previous one, it is tilted at 45 degree. And another port which is connected, and this also is tilted in the 45 degree. So there is a twist used, or transition we can say, from circular waveguide to rectangular waveguide. So one transition is there, that is one transition is there, that is what? Here this port, it shows this also is at 45 degree, and this is a transition which is used from the circular waveguide to the connection for rectangular waveguide. So here we see this waveguide is connected like this, and this is connected like this. So if we say this is one transition, this is transition practically for circular waveguide, circular waveguide to rectangular waveguide. With a twist of 45 degree. Here also this port, here this also is a transition, that is from rectangular waveguide to the circular waveguide. So rectangular waveguide to circular waveguide without a twist. So here we will use the dominant mode and the wave. Here we see the propagation of the waves in TE10 mode, TE10 mode propagation. The wave, EM wave, will have electric field vector perpendicular to the direction of propagation, and this, for easiness, for convenience, we are taking electric field vector, and this electric field vector, when it is perpendicular onto the plate, metallic plate, we can say metallic plate, where the boundary condition says that the normal component, here we have to see that normal component of electric field will exist on the surface of metallic sheet. whereas tangential component becomes 0, whereas tangential component of electric field becomes 0. So for easiness we can say En will exist, it will not be 0, and whereas Et will be 0, tangential component of this electric field becomes 0. So then onto this metal sheet, the again EM wave will exist and it will be propagating when it is incident onto the surface of the ferrite rod, which is under the effect of magnetic field, which is under the effect of magnetic field, DC magnetic field, DC magnetic field. And this ferrite rod has been cut for a phase shift of, for a rotation of 45 degree from the reference. So this is the reference line. Suppose this is EI, this is EI, and suppose this is EI, and it is after this shifted in the clockwise direction, suppose EI dash, and this has been shifted by 45 degree. Now we see the wave, suppose this is our ferrite rod, and the wave component is like this, and the wave is traveling this phase shift, this ferrite rod will rotate this electric field vector like this, that is in clockwise direction, in clockwise direction, in clockwise direction. When it is moving directly from this, then as it is propagating, it will be tilting, it will be tilting, and for what angle it has been manufactured, for that particular angle, this wave will be tilted by 45 degree, as here we have specified. So this ferrite rod, we have specified that this will be tilted by 45 degree. When it is tilted by 45 degree, to remain it on perpendicular, to remain it to perpendicular direction, so this plate which was available flat here, it was flat like this, and this component is traveling like this, but from here it has been tilted by 45 degree. So this output plate also has been tilted by 45 degree to make this electric field vector perpendicular onto this surface of the plate. So here also it will be perpendicular. So 45 degree it has been tilted, so this will remain as 45 degree. So it is perpendicular onto this port, and accordingly this port 2, this also has been tilted by 45 degree. So make it perpendicular, to make it perpendicular onto this port, to maintain this mode, TE10 mode, and this port also. But what is happening here? This circulator has been placed it here. This is one transition has been placed onto this plate. It means this whole structure is inside the circular waveguide. We can say this whole structure is inside the circular waveguide. It is not in the rectangular waveguide. So this is in the circular waveguide, we can see. And then as we have seen, now this circular waveguide is having this structure inside it, or that is this structure also. It is inside the waveguide, that is circular waveguide. This also is in the circle. So plate 1, ferrite rod 2, and this plate 2, they are inside the circular waveguide, that is circular waveguide. And here for this rectangular port, it has been converted rectangular port to circular port. It has been converted with the same dimension of this a cross-sectional area, and this port and this port will be fitted. They will be screwed. They will be fitted. Here the tension twist also is there, so we can say it is to be twisted. It is to be twisted also. So we can have one twist of 45 degree. So we can have a twist of 45 degree. Twist may be there. And it may be connected. So this is a twist of 45 degree. So it can be connected like this. So what is being done? That when the wave is propagating from source side, here we have said the source is available at this port. Source side. As we see in our lab, already we have seen that source is nothing in the microwave test bench, that is reflex klystron is available. Reflex klystron is available. But if we see the load side, if we see onto that, one frequency meter has been connected, and after that frequency meter, one variable attenuator is connected. Then after that variable attenuator, one antenna is connected. If we recollect that position of the isolator, then see that what is happening. The wave, when they have to move from the source side to the load side, then this will be maintaining T10 mode with a conversion of, when the wave propagates here, then the wave is converted into the T11 mode. That is dominant mode. This is dominant mode of the circular waveguide. Dominant mode. And again, this is going to be converted into this T10 mode. But what happens? Suppose when the mismatch occurs, now suppose at the load side, suppose this is source, and this we have connected our isolator, and this, suppose this is load, and source impedance is Z0. If load impedance and source impedance, they are not equal. If they are not equal, means here the load is antenna. Here the load is antenna, as we have seen in our lab. Antenna is the load. Suppose antenna's impedance, when the antenna's impedance and reflex klystron impedance, when there is a mismatch between the impedances, when they are not exactly matching, then some of the power will reflect from here and it will propagate through this isolator, and this isolator will prevent this wave to reach here, and it will not be reaching onto the source. Ideally, if this is providing full isolation, then this will not be reaching, this reflected power will not be reaching towards this, and then forward power will be routed. If the interaction is taking place from the reflected power and the forward power, then the standing waves are created. That's why the SWR increases. So whenever in the practical field also, whenever the impedance mismatches, then the reflections occur, and those reflections may degrade the communication property. They may degrade the communication, or the power may not be fully transferred from our source towards the load. So for that prevention, how it is preventing now? Let us see. It has made forward direction, that the electric field or EM wave or power which is containing electric field and magnetic field vector. Here we have shown only the electric field vector, we have not shown the magnetic field vector, as we have considered the vertical polarized waves, vertically polarized waves, and here they are creating, that is T10 mode, and this wave is moving in this direction, and it is from here also it is moving at the same 90 degree for the load set. So when it is reflected back due to the mismatch, then it will have the same dimension. The power will be like this only, that is 45 degree. This is incident power I, and this is I dash reflected power. Suppose we say onto this direction, that is 45 degree it has transferred. Now suppose it is moving, so this is again 45 degree, it is tilted, so it will be only same, it will be on, or it will be maintaining its orthogonality, means it will be perpendicular onto the surface, and when it is traversing through this ferrite rod has been meant for providing a rotation in the clockwise direction, whether it transfers from left side to the right side or right side towards the left side. It will provide the rotation towards the clockwise direction. So when it is transferring and coming onto this port, then the wave will be moving from here at 45 degree. Again it is tilting here. Suppose this is 45 degree, and then it will tilt. This vector will be tilted, or this vector will be rotated by 45 degree more. That is by 45 degree more. And this is, we can say, EI dash reflected. If I say EI dash reflected power with reference to this, then this will have EI dash reflected power in this way. So what is happening now? From the previous condition, it is total angle of 90 degree it has traveled. When it has traveled 90 degree, it means what? This field which was in the forward direction, and this is in the reverse direction, this field component becomes parallel and tangential. This EI dash R reflected component, it becomes parallel or it becomes tangential onto this plate, metallic plate. And here what we have said, that when the tangential electric field comes onto the plate, then it becomes 0. This is boundary condition, that tangential electric field becomes 0 when it becomes tangential onto the surface of the metallic sheet. So it means what? This power has been terminated. This power or this field has been diminished up to a very low level, and now this is terminated totally. This is finished. Now no power will be available onto this field. So this EI dash IRT tangential field becomes 0. So no power is available here. So reflected power becomes 0. It means what? That the forward power is propagating, but when the reflection is taking place, then the reflected power, when it is traversing through this ferrite rod and it is having the same direction rotation in the electric field vector, and that electric field vector becomes tangential to this plate, and this tangential component, it becomes 0, as this is the metallic sheet. So this component, when it becomes 0, so the power is, reflected power is becoming 0. So in this way, this isolator is saving our source when the reflected power is 0, when the reflected power is 0, forward power we say that is maximum, then ideally this device is saved, means the source which is used to generate the power, it is not going to take the power. So likewise, this source is saved or prevented from the damage. So we can say the power source which is connected at this port, we can have the connection onto this port of the source, that is reflex klystron, that will be saved from the reflected power. That's all. Thank you.
Shambhunath Group of Institutions, a mentor for glorious transformations.